Hello, my name is Mari Jensen. Welcome to this presentation of the PicoBlaze microprocessor. After watching this presentation, you will be able to describe in short terms what a PicoBlaze is, explain how to transform an FSMD into a general-purpose hardware platform, and explain the organization and characteristics of the PicoBlaze microcontroller. The PicoBlaze processor is a fully embedded, compact 8-bit RISC microcontroller core for the Xilinx FPGA devices. As it is a cell-level HDL description, it can be synthesized along with other logic. It is optimized for efficiency and occupies only approximately 200 logic cells. It is compact and flexible and can be used for simple data processing and control. It is particularly well adjusted for non-time critical housekeeping and input-output operations. Because it is easily integrated into a larger system, it adds another dimension of flexibility to an FPGA-based design. Throughout this and the following video, I am going to explain the PicoBlaze's organization and instruction set, as well as mention some examples of its applications. Note that most of this information relates to the KCPSM3 module and not the newer version KCPSM6. I will, however, mention if there are improvements made relating to the newer version. To create a basic skeleton of the PicoBlaze microcontroller, we transform a special-purpose FSMD into a general-purpose hardware platform. This is the diagram of an FSMD with a data path on the top. Here we see how all the components of the data path are tailored to the target application. Components such as the number registers, the routing of registers input and output, the number and types of functional units, and the control FSM. It may include multiple function units and routing parts. To transform this into our skeleton PicoBlaze, we begin by replacing the customized data path with a fixed configuration to make it more general purpose. We use a register file to replace the data registers and routing networks. This register file has a fixed number of registers and contains only 2 read ports and 1 write port. The function units are replaced by an arithmetic and logic unit, an ALU, which can only perform a set of predefined functions. This data path can now perform real-time functions for us. Next, we change the FSM part of the FSMD into a programmable state machine. Let's quickly recap what an FSM consists of. It has a state register which defines which state we are in, the current state. It has an output logic which defines which output signals to activate according to the current state, and the next state logic which determines the new state. These operations are modified as follows by the programmable state machine. The state register is replaced by the program counter, which then represents the current state of the control path. A sophisticated output logic circuit is created by implementing an instruction memory and a decoding logic. The output patterns created by the state logic and its effect on the output signals are encoded into instructions and stored in a memory module. This module is called a program memory or an instruction memory. A memory address corresponds to a state of the program counter. The decoding logic fetches the instruction from the memory address which the program counter points to and encodes it to generate the control signals. A simple next state logic circuit is made up by an incrementer and an associated multiplexing logic. As a programmable state machine has a sequential execution, the next state is usually the value of the current state plus 1, i.e. the program counter is incremented by 1. This sequential execution may be altered by different special instructions, which may load the program counter with other values. And we will get back to these specific instructions later. When these changes have been performed, we now have our skeleton of the PicoBlaze. That is to say, it is now the general purpose hardware platform we wanted, which can be used for any application. To customize the system, we now need to develop a new sequence of instructions and load these into the instruction register. Now for the basic organization. This is a somewhat simplified block diagram of the PicoBlaze, which shows us most of the features it contains. Here we can clearly see how it is based upon the previously described microcontroller skeleton. Down here are the parts that replace the next state register, the state register and the output logic of an FSM. As the next state logic, here we have the incrementer, a 31-word stack, which is to support the call return functions and some multiplexing logic. This program counter replaces the state register, and this instruction memory and decoding logic replace the output logic. However, the instruction memory is placed outside this processor module and created as a top-level HDL module called an instruction ROM. We will come back to this later on as well. On this next part, we see the register file, containing 16 8-bit general purpose registers and the 8-bit arithmetic and logic unit with the carry and 0 flag. I want to add that in the new KCP SM6 module there are now 2 banks of 16 general purpose registers. On top here we see the added data memory. This is a 64-word data memory called a data RAM. It is used to store additional data. As you can see, there is no direct path between this and the ALU. Therefore, any data must be fetched to the register file and stored back to the data RAM. Just to make a quick note that this is known as a scratch RAM in the Xilinx literature, but more or less everywhere else it is called a data RAM. To mention some additional general features and improvements of this processor, it has an 8-bit data width. The instruction ROM has an 18-bit instruction width and a 10-bit instruction address, which supports a program up to 1024 instructions. An 8-bit port ID signal is used to identify a port. Thus, it can support up to 256 input and 256 output ports. There are 2 clock cycles per instruction and 5 clock cycles for interrupt handling. There is an added circuit for interrupt handling, yet this is not shown in this diagram. Handling interrupts will be explained in more detail in another video. The PicoBlaze system is organized into 2 top-level HDL modules during synthesis. The PicoBlaze processor is represented as the KCP SM6 module. This was the original name of the PicoBlaze, though with a different number, and stands for Constant Coded Programmable State Machine. As mentioned previously, the second HDL module is the instruction ROM. This is made by storing the compiled assembly code to memory in advance of synthesis and configuring it as a ROM in HDL. In the next presentation, I will explain the instruction set architecture and the applications of PicoBlaze. Thank you for your attention.